So today we are going to talk about triangle law. Triangle law of vector addition. So to understand this law, we will have to understand its statement and understand its proof. So in order to understand its statement, first of all, let's write the statement. So it states that um, if so if two sides if two sides of a triangle taken in same order represents two vectors two vectors both in magnitude and direction. Then the third side of the triangle taken in opposite order represents the resultant of two vectors both in magnitude and direction completely. So if you just check out the definition or the statement, you will be very confused if you're like me. So to understand this much more clearly, I think a visual representation will be much better. So let's see. If two sides of a triangle taken in same order represents two vectors both in magnitude and direction. So let's first of all do this. Let's say I have a vector. Let's make this vector. Let's make it white in color and let's make it bigger. Let's say there is this vector which I will not represent by a letter right now, but just see it by the color. And I have another vector, suppose this. Let's make it blue and let's make it a little bit bigger. If we have these two vectors, then triangle law basically states that if both of these vectors, so let's go back, if two sides of a triangle taken in same order represent two vectors both in magnitude and direction, then the third side of a triangle taken in opposite order represents the resultant of the two vectors both in magnitude and direction completely. So we got the two sides of a triangle. So let's make it so that it actually looks like two sides of a triangle. So let's make this thing and let's make another. So when we say in order, it's like this. So think of a person is over here. He walks to here, then he walks to here. So that's in order. But if I keep it like this, it's not in the same order because a person walks here, then automatically jumps here, then goes here. That does not make sense, right? So basically, it must look like a path. So if you look over here, this looks like a path. So look at my cursor. A man walks from here and does not stop. So this is what we are talking about when we're talking about same order. Think of a man that does not change its path. I mean, it does not go back of sorts. So we got this. So let's go back to the definition. Two vectors, magnitude and direction. So I did not change the magnitude nor the direction. I only moved it by parallel transformation. And I represent it by two sides of the triangle. But since this is a triangle, let's complete the triangle and see what we get. Also, the second part says the third side of a triangle taken in opposite order represents the resultant of the two vectors both in magnitude and direction completely. If this is taken in opposite order, it means that this person goes from, look at my cursor, from here to here, and not from here to here, but rather from the opposite direction, since it is in the opposite order, which means it's like jumping. So it jumped back to the starting point and again moved. So, what does the triangle law actually state? It states that the resultant of this vector and this vector actually is the this vector, because this is a triangle. This vector and this vector are representing two sides of a triangle in same order. So this third side represented in opposite order is going to be the resultant. So now let's actually do the derivation of this and actually give them some labels, which will make it much more easier or much more manageable to do some calculations. So let's consider. Consider two vectors, two vectors A and B, which are which are represented which are represented by the sides by the sides by the sides OP and PQ of triangle OPQ. So just looking at the labels right now is a little bit confusing. So let's actually see the figure and label them. So we are considering two vectors, which is A and B. So in this case, this will be vector A and this will be vector B. So even after parallelly transforming it, this will still remain vector A and this will still remain vector B. And we said that A will be represented by the side OP, so it will be, let's make it this color. It's gonna be OP, and similarly, this side, other side B is going to be represented by PQ in the triangle. So this will be P and PQ. So in the triangle OPQ. Makes sense, right? So this was the first part. Also, let um, let angle between let the okay. So let's let the angle between vector A and vector B be theta. So we just defined what will be the angle. So a question that you might have is, since we have not connected any in this figure, we have not connected the vectors by head or tail method. So not by head or head or tail method. We have no place that we could have written where the angle theta must be useful. You might have a thought like that, but just look over here. If we are pretty sure this is the angle theta by tail method, right? So if I just move this backwards, what do you see? You just see if I drew a straight line that passes through, so like this, so it goes through A vector. So let's actually make it dotted line, which will emphasize that this is not that we are just trying to show the angle. You see that If it's passing through A, the angle will still be between this line, dot line, and vector B. So the angle between vector A and vector B is same as the angle between the vector B and the dotted line. I think this is pretty clear to understand. So also, let's go to the next part. So we did these two sentences. Now the third one is according to the according to triangle law according to triangle law of vector addition, the the third side OQ represents the the resultant of vector A and vector B, which means that if we call the resultant as R, so I will say that the resultant is vector R, it means this is the vector addition of vector A and vector B. So this is vector addition. So this does not work like normal algebra. So you can actually see in the figure. So this line OQ, represents the resultant. So let's call this resultant R. So R is just vector A plus vector B. So as you can see, it's not basically just adding the magnitude, since just adding the magnitude will be a much larger magnitude than the magnitude of the resultant that we got. So now we actually got through the background of sorts. So now, what do you think that we must find of our resultant? Since we pretty much know everything about vector A, vector B, and the angle between them, let's suppose that we know that. How would you find, what do you need to find of the resultant R, vector R? So if it were me, I would say that first of all, you definitely need to find the magnitude and also find the direction. So you need to find the magnitude and the direction of R, vector R. Why? Because it a vector is defined by its magnitude and direction. So if you have its magnitude and its direction, you basically have everything else. So now, um, let's actually try this. So now, first of all, let's find the magnitude. So the magnitude of vector R, it's gonna be, so before that we must do something. So OP is produced OP is produced and dropped perpendicularly from Q at N. So to understand this, let's actually read the statement that I'm talking about. So OP is produced and dropped perpendicular to Q at N. So let's go back here. So OP was produced. This line that I just showed you, actually I showed you to represent the angle, but this is the line that is being produced. Also, it also has written and drop perpendicular from Q. So from Q, let's drop a perpendicular. So the perpendicular, let's drop it. So this will be the dropped perpendicular. Um, just suppose that this is 90 degrees, even if it might be or it might not be. So I drop the perpendicular from Q and at N. So the point that it is dropped at, so the point at which it is dropped at, let's take this color. So this point is N. And this is a perpendicular, so this will be 90 degrees. So this angle between these two dotted lines is actually 90 degrees. pretty clear, I think this is. So now let's look at what we can do. So first of all, let's look at the triangle PNQ. Okay, so from um, from triangle PNQ. So looking at PNQ, I will actually just make the triangle. So let's see. There is a vector B. I definitely see vector B. I see PN and Q. I see theta and I see a 90 degrees. So if I have to create a triangle, I think that's pretty easy. It's not going to be the exact triangle, but it's basically going to be the representation of this, which means the figure might not be to scale or stuff like that. So if this was the triangle, let's go back. There is vector B. So this will be vector B. So let's actually make the... So instead of making the vector B, I will just make it like a magnitude of sorts, since we don't need the vectors right now. Since we are talking about magnitude, we will only discuss about the magnitude. So this will be the magnitude of B, which I can just write as B. Or we can write it as vector B with some modular signs around it. Or also, let's go back and we see that this is P and Q. So let's add that as well. So this is P, N, and Q. Also, there is this 90 degrees and theta right over there. So we have an angle of theta and 90 degrees, right? So now let's do some math. Okay, so from triangle P and Q, um, do you know what will be sine theta? So sine theta. So sine will always be perpendicular by hypotenuse, P by H. So from here, this will be the base, this will be the perpendicular, which means QN is the perpendicular. And let's go here, hypotenuse will be the longest side, so B will be the longest side. So let's just write this side length, PQ. I think this is pretty clear. So make it much more clear, let's actually even write it out. So this, the longest side is obviously going to be the hypotenuse. And the side connected with the angle is going to be the base. And the side that is not connected with the angle is going to be the perpendicular. So this is what we have. So over here, we know the value of PQ. So QN, and we get PQ will be B, right? Since PQ is B. So this means QN is just going to be B sine theta. And this will be our equation 1. So this will be useful pretty soon, and we will know about that why, but this is pretty clear, right? So any of the steps, like most of the steps that I'm doing, can actually be repeated in some other fashion as well. So I could actually have done this in the end and not much problem would arise from it. So let's again go to the next page. And similarly, we did of sine, but who says we only have to do of sine? We can also do of cos. And why are we doing this? You will find out pretty quickly. But so cos theta, it's gonna be B by H. So it's base by hypotenuse, which means its base is Pn and hypotenuse is PQ. So we know the value of PQ is B, so it will be Pn by B. Okay, and this means Pn is definitely equal to B cos theta. And this is our equation number 2. So I think this is pretty clear for right now. So now let's look at, so again, from triangle O and Q. So what is O and Q? So O and Q. We're taking a look at this triangle as a whole. So let's copy this instead of making it once again. So this is the triangle that we are looking at right now. Let's make it so that this is exactly in line. So if it's necessary, I will also make a simplified figure, which will be much more clear than this, but this will do for right now. So in the triangle O and Q, let's actually use the Pythagoras theorem. So the Pythagoras theorem says that the longest side, which is the longest side? OQ is the longest side, since this is the right angle triangle. So we can say OQ squared, let's actually write with this color. OQ squared is equal to perpendicular square. So I can take any as perpendicular since there is no defined angle. So perpendicular square, let's say it's ON. So perpendicular squared plus QN squared. So it's B squared. Now we can write ON as OP plus OPN, right? So let's actually write that. So OQ will remain the same. So OQ will remain the same. ON will be written as OP plus PN squared plus QN squared. Just think about it. OP plus PN will just result in ON. Since we're talking about lengths, Pythagoras theorem actually talks about the lengths. So lengths over the numbers. So this works. Now let's just change the things that we know. Okay, so we know OQ. So let's look at OQ. If you're just taking the magnitude, OQ will just be R, right? So OQ will just be R. Let's write it with the same color. No need to make it difficult. So this will be R. OP will just be A in terms of magnitude. And PN will just be, so let's go back. PN will just be B cos theta. So this will be B cos theta whole squared plus Qn. This part, it's just gonna be Qn, so equals B sine theta. So this will just be B sine theta whole squared. So now let's just open up everything and see what we get. So we get R squared must be equal to A squared plus 2AB cos theta plus B squared cos squared theta plus B squared sine squared theta. So the question arises, why? So this is just the expansion of A plus B whole squared, which is just A squared plus 2AB plus B squared. And now you can take B squared common from here, and you will get B squared bracket sine squared theta plus cos squared theta. So actually sine squared theta plus cos squared theta is 1, which means if I took B squared common, so let's say R squared equals A squared plus 2AB cos theta plus B squared, and the part that I take common will just be 1, so no need to write that, right? So we got the result of the magnitude of the resultant. It's just gonna be A squared plus B squared plus 2AB cos theta. So in other books, or you will see other notations as well, where A and B might be represented by some other letters, and R might be also represented by other letters. And that's just some um, things that you don't need to worry about. Just understand the main concept. So I'm trying to teach you the main concept. So this is the magnitude of the resultant. Now let's actually conclude this. So to conclude this, let's call this equation number 4 or 3. I think it's number 3 right now. So let's call this number 3, and let's just see. So um, let's actually copy this if I can. Maybe not, but so I was actually trying to write it over here, but since there's no space, I'm gonna write it over here. So equation 3 is the required expression is the required expression for the magnitude and direction, for the magnitude of resultant vector, since we just found the resultant. So we found the magnitude of the resultant. Now what do you think is something important that we must find out? I would say the direction. So let's talk about the direction. So the direction of vector R, or the resultant. So before that, we need to do something. So let phi be the angle phi be the angle made by vector R with vector A. So we are just supposing that this is the angle made by vector R and vector A. So let me go back to the figure. This is the original figure. So the angle between R, so this is, the red one is R, the white one is A. So the angle between them, so let's make it another color. So it's gonna be phi. So this is the angle phi. So why did we take it with vector A and why not with vector B? The simple answer is you can't take it with vector B. It's just gonna lead you with another formula. So we took vector A because I wanted to, and taking it with one of the vectors helps us because we already know everything about vector A and vector B that we are supposing. So which means if I know the angle phi by which it is with by so it's the angle between the resultant and vector A, I definitely know what the direction of resultant is with respect to A, which means um, I just know the direction of vector R if I know the direction of vector A. So this is why we need this. So now um, let's do some things. So from triangle O and Q. So let's go back. Let's look at this one. So I don't want to go all the way back. So O and Q. It's actually this big triangle. So let's just copy this big triangle and keep it right over there. So this is the big triangle. Also there we need to add the angle phi over here. So let's do some math. So let's take a look at tan. So tan phi, what is it gonna be? So tan phi is gonna be P by B. So P, let's say this is P, since we have mentioned an angle, so we will have to take it in consideration to this angle. So this will be QN by B, which will be ON. And now let's actually do this in another page. So Next page. So we had tan phi. So let's actually write it above. Tan phi must equal Qn by P. Oh, sorry, O n. Let's just copy this as well, so it will be very handy for us to do this. So let's just look at what ON is. So ON, let's actually move this over here. So ON, it's just OP plus PN. So QN by OP plus QN by OP plus PN. I think this is pretty clear right now. But also, if you remember, when we found the magnitude, we described all of these terms. So Qn was b sine theta, OP was vector A, so which got lost somewhere. Let's vector A and also write over here. So vector A. So this was Qn was b sine theta and OP was just A. So OP is A plus Pn, which is b cos theta. Right? So this expression is not actually the this is not what actually gives the direction. I mean, technically gives that direction. It's just that I find this equation much more easier to manipulate or to talk about rather than the actual value of phi. So now let's call this equation number 4, and the actual angle that you need to find is actually just phi. So let's go write it phi. Let's actually write it this right over here. So phi will just be tan inverse this expression. So b sine theta sine theta by a plus b cos theta. So to remember this formula, since this formula is not that simple or easy to remember, you can remember it like this. So sine theta by cos theta is just going to be tan theta. So you can remember like that, this part, and the angle which you are making it with is going to be, so since we are making the angle with A, the A is going to be over here and B is going to be over here. But if you made the angle with B, B would be here and A would be over here. So I hope you got the kind of the trick that I actually use to remember this formula. It just makes it much more easier to remember. So let's call this equation number 5. And so equation 4 and 5 gives the direction of resultant vector of resultant vector. Truth be told, it actually represents the angle between resultant and vector A, but the angle that it gives also helps us to find out the direction of the resultant. So we got to this point. Now let's actually take some uses, or let's take a look at the formulas in some special cases. So let's take a look at some special cases. So the first case is when two vectors, so when two vectors are acting in the same direction, in the same direction. So it will mean that theta, the value of theta is 0 degrees. So to understand this, let's just take some vectors. So this, let's suppose this is some vector. Let's call it A in this case. So let's actually just make it so that it looks like our original figure, just a little bit changed. I think this was blue. Wait, 60 degree, sorry, 6 pixels. Let's move it over here. And this was vector A, this was vector B. Both are in the same direction, both have a angle between them 0 degrees. So now let's look at from equation 3. So if you don't remember equation 3, I won't blame you, but the equation 3 was the resultant, so the magnitude of the resultant. So I think you might have an idea now. So the resultant was r with under the square root a square plus b square plus 2ab cos theta. But we just know that, but we just found out the value of theta. And what was the value of theta? The value of theta was 0 degrees. So a square plus b square plus 2ab cos 0 degrees. So what is cos 0 degrees? Cos 0 is just 1, which means cos 0, this part is just 1. So let's write it over here. Cos 0 degrees is 1. So now we just have a square plus b square plus 2ab. So square root a square plus b square plus 2ab. So if I were you, I just saw a very recognizable formula, which is of a plus b whole squared. So let's just write that. R equals to square root of a plus b whole squared. This is a very recognizable formula. So now the square root and the square will cancel out, which will lead us with r a plus b. So this is the maximum value. So this is the max value. So think about it. If two vectors are in the same direction, then the magnitude of the resultant will be maximum. Also, from equation 4, so that was when we found the angle, from equation, let's do 5 rather. So we will just get phi. So phi was tan inverse b sine theta by a plus b cos theta, which will, now let's keep the value. So tan inverse b sine 0 degrees by a plus b cos 0 degrees. And sine 0 degrees is just 0. So 0 multiplied by something is 0, 0 divided by something is 0, so this whole term just turns out to be 0. So tan inverse 0 is just 0 degrees, which will tell us, so let's go to the next page. We have phi must be equal to tan inverse 0, so phi must be 0 degrees. So the resultant will have the same direction as that of the given vectors. So this is what we found out. So if this were the two vectors, obviously the resultant would be something like this. Let's parallelly transform it. So let's move it. Think of this as it is in the same size, or like pretty much the same size. So this will be the resultant. I think this is also pretty clear. So let's look at some other cases as well. This is the case for maximum value. Another case that I want to look at is for when this is at 90 degrees. Of course, this formula is valid for any case, but we are just looking at some special cases. So when two vectors are adding perpendicular, oh sorry, are acting perpendicular to each other to each other, so which means the angle of theta is just going to be 90 degrees. So let's actually just look at how you represent this. So we will have a vector a. Let's say this is vector a. No reason for why this is vector a, just gonna say that this is vector a. And let's make our another vector b. So let's change the color, it's blue. And we have a vector b. So they are acting 90 degrees. So just by making the triangle, we're pretty sure by triangle law that how will the resultant look. And I'm also gonna make the resultant to make it much more clear. So this will be the resultant. So it must be taken in opposite order. I'm taking it in opposite order. I'm already doing this to give you a hint of what is actually going on. And this is gonna be 90 degrees. So this angle is 90 degrees. I think the picture is pretty self-explanatory, and the results that we get is also pretty interesting. I find the results very fascinating. So let's have a look at this. So from equation 3, we just have r equals square root a square plus b square plus 2ab cos theta, right? So instead of writing cos theta, I'm just going to write cos 90 degrees. And cos 90 is 0. So cos 90 is 0. If there is place, I'll write. So cos 90 degrees is 0, which means this part will just cancel out or just disappear, let's say. Which means we will get r must be square root a square plus b squared. This should look very similar to the Pythagoras theorem, and it's basically like the Pythagoras theorem since you're just taking the magnitudes, so it will just be the Pythagoras theorem, right? And now let's take a look at the direction. So let's do it in another page. So from equation 4 or 5, I think 5, we have phi must be equal to tan inverse b sine theta, so b sine 90 degrees by a plus b cos theta, which is 90 degrees. Oh, sorry, I actually forgot to show the angle 5. So like if I did not show it, like what am I actually making? So this is phi in this case, so it's the angle made with vector a, and also here phi is the angle made with vector e. So this phi will also be 0 degrees. Pretty self-explanatory. So we got this. Sine 90 will be, where should I write it? Let's write it over here. So sine 90 is actually going to be 1. So phi will be equal to tan inverse b by a, Why was it b by a? Since cos 90 degree is 0, so that part will go away. So this is the expression. And if you look at this expression, I think you might also find this expression very similar to the formula of tan theta. So tan theta will just be p by b. So p is b and b is a. So the perpendicular is b and the base is a. So that's why it was b by a. Now finally, the third case and the final case that I'm going to talk about. So the third case is actually when two vectors are acting in opposite direction, which means theta, or the angle between them, is 180 degrees. So to do this, we just have to draw the figure, and I think the figure is pretty simple, to be honest. So if this is vector a, then we just have to rotate this to make this vector b. And if you actually look over here, the resultant actually depends on which is bigger. So you will actually see this in the results. So right now, let's say b is bigger, then I would say the resultant will be going in this direction. But if the resultant was smaller, the b vector b was smaller, the resultant will go in this direction. So let's make it like this to make vector a bigger in this case, but there might be two cases on this. So it depends on which one is bigger. Let's actually make both the cases so that you actually have a glimpse of what I'm trying to say. So let's make this side bigger and vector a little bit smaller. So in this case, let's see where the resultant will actually be. Since b is gonna cancel some of this, it's obviously gonna be smaller. And actually, let's change the color to red. And similarly, in this case, it's also gonna be a little bit smaller, since a is also gonna pull it back. So this is just visual representation, and this will be our resultant r in both cases. And the angle between them is obviously 180 degrees in both cases. So let's start from equation number 3. So from equation 3, we know that resultant r is gonna be a squared plus b squared, a squared plus b squared plus 2ab cos theta. So cos theta is 180 degrees, so its theta is 180 degrees, and cos 180 degrees is actually minus 1. So obviously, why these values are like them, you should have learned in math class, which I might teach you or I might not teach you. Depends. So let's actually continue with this. So we have this. So 1 minus 1. So sorry, minus 1. If it's gonna be minus 1, then we will just have to keep a minus over here. So we will have r is equals to square root a square plus b square minus 2ab. So this also might look like a very recognizable formula, at least for me it does, which is the formula of a minus b whole square. So r is gonna be square root of a minus b whole square, which means the square root and the square cancel out, which means the resultant will just be a minus b, which is the minimum value. So sorry. So this or okay, sorry. So this or so why do we have to talk about two cases? That's pretty simple. If A is bigger, then this will be the answer. So if A is bigger, so this first case. But so let's just add or or but in some cases B might be bigger, right? So either A or B, someone might be bigger. So you have either A minus B or B minus A, depending on which is bigger. So this is the minimum value, and this is the minimum value, and there is a little bit caveat to it, which is this depends on greater value. So this is a pretty unique fact about the opposite direction. So let's make this green color. Okay, now let's talk about the angle. So from equation 5, we have phi equals to tan inverse b sine theta, which is 180 degrees, by a plus b cos theta, and sine 180 degrees. So sine 180 degrees is actually 0 as well. So as a whole, this will be 0. So it's phi equals tan inverse 0. So a question arises. We also got tan 0 when we were talking about when they were acting in the same direction, so when they were 0 degrees. So what you would think is their answer will only be 0 degrees. But since the subtraction actually leads us with true result, and we have already seen that it does, we must also take the other possibility, which is that this could also be 180 degrees, since tan inverse 0 can also lead to 180 degrees. So this also depends on depends on greater value. So both the cases depends on greater value. So these were the cases that I wanted to talk about. Till now, we only talked about the angle made by resultant with A, vector A. But who says you only need to make it with vector A? So let's take a look at a note. So you might have a question, what will be the formula when you make it with angle B? Let's just see. So if alpha is the angle made by vector R with vector B, then so let's actually just make the figure, because I don't think the figure is going to be that hard. So this is red, since let's make this the resultant. Not the exact figure, just trying to replicate it to my best of my abilities. So let's make this go from here to here, and finally vector A, which are represented by white. But there is no need for me to represent them by color. It's just to make my life a lot more easier and easier to explain. So this is vector A. This was vector B. And this is the resultant R. So if alpha is the angle made with R and B, so is this the angle? Yes, this is the angle alpha. Why? Since it is connected head by head. So here it was tail by tail connection. That's why we call this angle theta. Not because they are connected by tail, or because the angle between them is measured when you are measuring them by tail. This will be theta, this will be alpha. So to actually get a sense for this, I'm gonna write it down over here. So we know tan theta. If you remember tan theta and the trick I told you, the angle you are making it with. So you are making it with A. So add A to the bottom. And whatever that you are not making it, keep it at the top. Then since there is tan theta, just keep sine theta. Sorry, this is phi. Yep, this was phi. Sorry. Since phi. And here will be cos theta. So theta is the angle made between A and B, not with R and A. So now, vector R and vector A. So now, let's just keep the same logic. So we have tan alpha must equal, the angle is made with vector B, so there will be B at the bottom, and A over here. Since this is tan, there will be sine theta by cos theta, and this is the result that you needed. Pretty simple, right? So this was it for today's video. Quite a long video, if I have to say so myself. So in the next video, we are going to talk about parallelogram law of vector addition, which is also long. Like, it's basically this. We are literally going to do this one more time. So till then, bye bye.